Let's walk through the TensorFlow Lite microcode to better understand the concepts described in the previous lesson. Our aim here is to understand the structure of the application-specific code and also to learn about the TensorFlow APIs. As you may recall, there are many different components involved in the keyword spotting application, starting with the initialization phase. In this particular screencast, I'm going to focus on the initialization stage. And I'm going to walk you through the different steps that are involved. And I'm going to do this in a lot of detail this particular time around. But in subsequent applications, I'm going to go a bit faster just because it's a repetitive template that you'll find you'll be using in many different applications. So looking at our IDE, the first thing you will see here is that there are a couple of header files. Many of these header files are all about the TensorFlow Lite micro. For example, line 26 through 31 are all about setting up the default TensorFlow Lite micro ops. And then there are a couple of application-specific files here. And now these correspond to activities that are part of the application architecture, which we'll go into later. One of the first steps is to actually declare the variables. So let's look at what the code says. Scrolling down a bit between lines 34 and line 50, what you see are the actual variable declarations that are needed. The first part of the code is mostly centered around things that are needed for TensorFlow Lite micro interpreter itself. There is an error reporter, which is responsible for logging errors. And you'll find this in almost every single application. And then there is the model pointer, which actually holds the flat buffer model that we need to load that corresponds to the application. For example, here we are interested in the TinyCorn network that does keyword spotting. Then there we have the interpreter itself, which we have to initialize with a certain amount of the required state. And where we have an input pointer for the input that's going into the neural network. And the next two correspond to actually the application specifics, which are about getting the features that are needed. In other words, where the spectrogram is sitting. And the output that comes out of this network, which is stored in recognized commands, which tells us if the keyword is actually recognized or not. More on the previous time later. And the second half of the variable declaration scope says that we first have to define the tensor arena. And now if you remember what I've said before, the tensor arena is extremely critical. And you have to size it appropriately if you do not want your application to crash with an error. So here you have experimentally determined what the size needs to be. And then you go ahead and allocate the tensor arena buffer, which here is set to 10 kilobytes. Then we allocate the feature buffer, which contains the actual spectrogram features, which we'll be using in order to do inference on. And it's of a certain size as well. And then we have the model input buffer. This is basically pointing to a buffer that will be initialized later in order to tell the interpreter where the inputs are coming from. The next step in our timeline is to actually load the model. So if I scroll down a little bit and go into the setup routine, which, as you should recall, is only executed once, you will find that there's a function called getModel. GetModel's job is effectively to take a pointer to a single dimensional array, which has actually got the flat buffer file schema, which defines a neural network model that we want to load and then run. And the next couple of lines are basically doing some error checking to make sure the schema version matches, because you always have to make sure that the network output file that you have in your schema is actually corresponding to the latest TensorFlow version that we'll be using. So this is quite standard, and I expect you to do the same. And after that comes resolving operators. Scrolling down a little bit further, you will see between line 79 and line 99, we have a chunk of code which is all about the op resolver. The op resolver is taking in 4 different ops here. Now, how do I know what the ops are? Well, you can look it up, look up what the ops are using the Netron app that I told you about earlier. And if you look at the network architecture using Netron, you will see that there are these 4 different ops. Now, if you do not know what the ops the network is actually using, let's say hypothetically you missed one of the ops, it's not the end of the world. TensorFlow Lite Micro will actually tell you through an error that you're missing one of the ops when you're actually trying to run it. So that's one of the ways you can easily figure out what are the other options that you could include with your ops resolver. As I mentioned, you have the all ops resolver, which is a cop-out way of doing op registration. In other words, if you do not want to explicitly register all the ops, you can easily just say, just use all the ops, bring on all the ops. But of course, as a TinyML engineer, at this point, you should know what the pros and cons are of bringing in all the ops. Bringing in all the ops is not necessarily a good thing because it ends up wasting a lot of space. So keep that in mind. And then you scroll down a bit further, you see that we are arriving to the next major step, which is the initializing the interpreter. Initializing the interpreter requires us to pass a whole bunch of variables in here, starting with the model that we're actually bringing in, what are the ops, where is the TensorArena, how big is the TensorArena, and what is the way by which we have to report errors. Once you have this bit of code here, you effectively are ready to start the interpreter. Then going back to our timeline, we see that the next step is to allocate the arena, which is happening in line 107. We are actually allocating the tensors. This is using the TensorArena space that we had previously told the interpreter to use. Once again, we do error checking as always. It's always a good practice to do that with each function. Finally, after that, we tell the neural network where the model's inputs are really coming in from. And that is happening between line 113 and line 123. So what we are asking the interpreter to do is to give us a reference to where its input buffers are actually stored. And you will see that it says the model input, has got a dimension of 2. Now you might be wondering, why does an input buffer have 2 dimensions? Well, the first one is purely a wrapper. That's why you're seeing that here. When we look at the dimensions of the data of the first element, it's only got 1 entry in it. And that single entry, which then if you poke at, you will see that just has a single size of 1. And subsequently, the second entry that's in there is actually our spectrogram size. In other words, it is a k feature slice count times k feature slice. So now if you remember how big our spectrogram is, it's going to be 40 columns wide, and it's going to be 49 rows in height. And that's what this is, the slice count times the slice size. And if we look that up, we'll see that that is declared as a constant. And you can see that there's a k slice size is 40, which is effectively our column size, and k slice count is 49, which is the number of rows that we have in our spectrograms. And so now if you go back up to our micro speech file, we're just making sure that the spectrogram dimensions, which we are going to be feeding into the network, are exactly the same as what the network is expecting. So this is actually what the network is expecting. And of course, we've got to make sure that this size is the size that we pass into it. And we want to make sure that the data type is correct. And it's not, a FP32, it's actually an int8 that we are passing in. And that's effectively what we are defining over here. Finally, the next step in our process is to set up the main loop. And in setting up the main loop, you can clearly see down here is that there are 2 stages. The first one is called setting up the feature provider. The feature provider is the one that actually accesses the audio buffer and generates the spectrogram. And that spectrogram is what we actually feed into the network later on. And after that, you do the inference. And that's when we go into recognize commands, which will actually help us recognize the actual output. So more on this later. For now, all you need to know is that we are simply setting up the variables. All right, with all that said, you should at this point be quite comfortable having gone all the way from declaring the variables to loading the model, to resolving the ops, to initializing the interpreter, to allocating the arena, to defining the model inputs, and then finally to setting up the main loop. This is the process that will repeat over and over and over in all the different applications. So get comfortable with it, and you will naturally be feeling comfortable with it as you start writing a little bit more code.